So here we want to determine whether the improper integral diverges or converges. And we have the integral from 0 to e of the natural log of x squared dx. Now the reason that this is an improper integral is because the function that we are trying to integrate here, the natural log of x squared, this function is not defined for the lower bound of integration, x equals 0. If you were to look at the natural log of x squared where x equals 0, watch what happens. We'd have the natural log of 0 squared, which is equal to the natural log of 0, and the natural log of 0 is an undefined value. The natural log function is not defined for x equals 0. In fact, the natural log function, not the natural log of x squared, but the natural log function ln x, is only defined for positive values of x, or values of x greater than 0. Now, in the case of the natural log of x squared, this would actually be defined for all values of x excluding 0. You could put in negative values of x, and then because they're being squared, you would still have a positive input into the natural log function. All right, but regardless, the natural log of x squared is still not defined for x equals 0. That's still going to be an undefined value. And so because that function is not defined at 0, which is the lower bound of this integral, we have an improper integral. And so in order to evaluate this integral or determine if it diverges or converges, we will have to make a slight adjustment to the integral. In particular, what we will have to do is introduce a limit. We will replace that lower bound of 0 with some other value. We'll just choose a letter such as a, and then take the limit as a approaches 0, and then see what happens to the evaluation of our limit as that lower bound approaches 0. But now before we do that, there is a nice simplification that we can make to this integral to make it a little bit easier for us to solve. What we can do is use one of the properties of logarithms to move this power of x to the front of the natural log function, right? Remember that if you have the natural log of a to the power of b, that's equal to b times the natural log of a. And that's true for all logarithms, not just the natural logarithm, okay? If you have some value raised to a power within the natural log function, you can take that power and multiply it by the natural log function, and then just have the natural log of the base, the natural log of a. All right, so we could take this power of 2, multiply it by the natural log, and just have 2 times the natural log of x. All right, that's going to make this integral a little bit easier to work with, in my opinion. So here's the first thing I'm going to do. I'm going to rewrite the integral like this. We'll have the integral from 0 to e of 2 times the natural log of x dx. But then in addition to that, I'm also going to move that constant multiple of 2 outside of the integral. All right, so I'll rewrite it like this. We'll have 2 times the integral from 0 to e of the natural log of x dx. And we still have an improper integral here, right? Because the natural log of x is still not defined for x equals 0, just like the natural log of x squared was not defined for x equals 0. So our integral is still an improper integral, and so we will still need to introduce a limit, which is what we are going to do right now. Here's how I'm going to rewrite this integral. We will have that this is equal to 2 times the limit as a approaches 0 of the integral from a to e of the natural log of x dx. All right, so I replaced that lower bound of 0 with a, and then took the limit as a approaches 0 for that integral. All right, now there's one more thing that I want to add in here yet to make this more accurate, and that is that we want to look at the limit as a approaches 0 from the right, okay? And let me explain why that's the case. The natural log of x, the function that we are now integrating, if you were to look at its graph, and we sort of already touched on this earlier, looks something like this, right? That's the natural log of x. It is only defined for positive values of x greater than 0. It's not defined for x equals 0. It will get really, really close to 0, but it will never reach the value of x equals 0, and it's also not defined for any negative values of x. Okay, and I should point out here that if you were to look at the graph of the natural log of x squared, it would look a little bit different than the natural log of x. It would look something like this. You would have a curve going this way and a curve going this way. That would be the natural log of x squared. And so this function is defined for negative values of x because they get squared and become positive, but this function is not. And so technically, when you move this 2 to the front of the natural log function, we should be putting absolute value bars around this x. We should have absolute value bars right here, but that's not going to be necessary in this case because we are not looking at negative values of x for this integral, right? We're looking at values of x from 0 to e, positive values of x. So since we're not dealing with negative values, we don't need to worry about those absolute value bars. Okay, I just wanted to make a quick note about that because that might become important for other integrals. Okay, but back to my point here, we need to look at the limit as a approaches 0 from the right for this integral because the natural log of x is only defined for values of x from the right of x equals 0. We can't look at the limit from both sides of x equals 0 because the limit only exists on one side. All right, I hope that makes sense. We want to look at what happens for this integral as that lower bound approaches 0, but for the natural log of x, it only makes sense to look at the values of x getting close to 0 from the right side. So that's why we're looking at the limit as a approaches 0 from the right. Okay, now let's continue on with evaluating our integral. We now need to discuss how we are actually going to integrate the natural log of x dx. And you might recognize this to be an integral that we can very easily solve using integration by parts. It's usually the case that if you were solving an improper integral that you've already been introduced to integration by parts, you know how to use it. And when you learn about integration by parts, you are usually shown that you can integrate the natural log of x dx by using that method, just like you can use it to integrate the inverse sine function. And if you've never seen that before, be sure to check out my lesson and examples videos on integration by parts. But even if you haven't seen it before, here's how it works. Remember the formula for integration by parts looks like this. It's u times v minus the integral of v du. And for this integral, where we have the integral of the natural log of x dx, we set u equal to the natural log of x and set dv equal to dx. All right, and so then we take the derivative of u and integrate dv. So we get du dx, the derivative of u with respect to x, is equal to the derivative of the natural log of x, which is just 1 divided by x. And then what we want to do is solve for du, because we're going to need that, as you can see from this formula. So we want to multiply both sides of the equation by dx. And so we'll have du is equal to 1 divided by x dx. Okay? And then to take care of dv equals dx, we want to integrate both sides. We'll have the integral of dv is equal to the integral of dx, which gives us that v is equal to x, right? In both cases, we're just integrating 1, but we're integrating with respect to different variables. The integral of 1 dv will just be v, and the integral of 1 dx is just x. Okay, and so now what we can do is rewrite our integral using the integration by parts formula, and you'll notice that the resulting integral here will be something that we can easily integrate. All right, so here's what we're going to have. This will be equal to 2 times the limit as a approaches 0 from the right. And because we're splitting up this integral into two different terms, here's what I'm going to write. We're going to have brackets around what we're going to write out, and we're going to be evaluating that from a to e. And you'll see what I mean when I write it out. For now, let's write u times v minus the integral of v du. U is the natural log of x, and v is x. So we have the natural log of x times x, and then we are subtracting the integral of v du, so we'll have x times 1 divided by x dx. All right, so we have x times 1 divided by x dx. And then all of that is going to be evaluated from a to e, okay? And then, of course, all of that is still contained within this limit. We are taking the limit of this entire expression because this is just this integral written in a different way, okay? And so now what we can do is a little bit of simplification. Notice that we have x times 1 divided by x in this integral. Those x's will cancel out, and we're just going to be left with 1 dx in this integral, which is really nice. That's why integration by parts is helpful here. And so let's perform that simplification. We don't need this integration by parts work anymore, so I'll erase it. And we will continue our work up here. This will be equal to 2 times the limit as a approaches 0 from the right of x times the natural log of x minus the integral of dx, and we are evaluating from a to e. Okay, now the integral of dx is just x, so now we'll have that this is equal to 2 times the limit as a approaches 0 from the right of x times the natural log of x minus x, and then we are evaluating from a to e. Now we can evaluate this expression at e and subtract the evaluation of this expression at a. All right, so if we do that, this will be equal to 2 times the limit as a approaches 0 from the right of e times the natural log of e minus e. That is this expression evaluated at e. Now we want to subtract evaluating it at a. So we'll have minus and then put this in parentheses. That negative needs to affect both of those terms. So we'll have a times the natural log of a minus a. Okay? Now we can simplify. Remember that the natural log of e is just equal to 1. So this will be equal to 2 times the limit as a approaches 0 from the right of e times 1. So that's just e, right? E times this is just going to be e. This is just 1. But then we have e minus e, right? We have this e minus this e. So those are just going to cancel out to become 0. So actually, here's what I'm going to write instead. These two terms cancel each other out, and so we are left with 0 minus a times the natural log of a minus a. So I'm going to distribute that negative to both terms. So we'll have negative a times the natural log of a plus a. Okay? So now, technically we don't need that 0, so I'll just erase that, and we'll just have the limit of negative a times the natural log of a plus a. And so at this point, I think it makes sense for us to try and evaluate this limit and see if our improper integral diverges or converges. And so we can just plug 0 into this expression for a and see what happens. You can always do that for a one-sided limit, just like you can for a two-sided limit. And so if we do that in this case, this will be equal to 2 times negative 0 times the natural log of 0 plus 0. Now, this term is not a problem. The limit as a approaches 0 from the right of a is going to be 0. That's not a problem. We don't need to worry about that. But this part right here is a problem. We have 0 times the natural log of 0, but if you remember our discussion from earlier in this problem, the natural log of 0 is an undefined value. We don't know what that is. The natural log function is not defined for x equals 0, and so that is a problem. We can't say that that is equal to some finite value. We don't know what it is. However, we can look at it from the limit perspective of what is happening as that value of a gets close to 0 from the right. In other words, what is happening to the natural log function as we look at positive values of x getting closer and closer to 0. And if you remember the graph of the natural log of x, I drew it out earlier, but I'll draw a smaller version of it here. It's just a curve that looks like this. And so as you look at smaller and smaller values of x getting close to 0, you can see that the y value of the function is getting smaller and smaller towards negative infinity, or you can think of it as becoming a bigger and bigger negative number. All right, so really, as a approaches 0 from the right, or as x approaches 0 from the right for the natural log function, it is reaching towards negative infinity. All right, so from a limit perspective, that's what we can say. We can say that this would be equal to 2 times negative 0 times negative infinity plus 0. But we don't really care about that plus 0. That's not a problem. What actually is still a problem is what we have right here. 0 times negative infinity. You might be tempted to say that that is 0, but you can't say that. We don't know what 0 times negative infinity is. This is an indeterminate form for a limit. When you see 0 times negative infinity, you cannot say that that is 0. We're going to have to go back to the limit and manipulate it in some way so that we don't get that indeterminate form. All right, we are not allowed to assume here that that is equal to 0, and 0 times 2 is 0, so the integral must be equal to 0 and converge. We can't say that. So we have to back things up here and go back to our limit and figure out a way to rewrite this limit in a way that we can evaluate it. And so what can we do here? Well, for one thing, remember that we don't need this term of a. These are two separate terms for this limit. Remember that if you have the limit of two terms being added together, you can take the limit of one term, add it to the limit of the other term. So technically we could split this up into two limits, and the limit as a approaches 0 from the right of a is just 0. So we don't need to worry about that term, that just kind of disappears. What we're really looking at here is 2 times the limit as a approaches 0 from the right of negative a times the natural log of a. All right, this just becomes 0. But as we discussed, we are currently in an indeterminate form for this limit, so we need to adjust it in some way. And so what we can actually do here is multiply by a form of 1 of the reciprocal of a. That's going to help us out here. And I think you'll see why once we do it. Here's what I'm suggesting we do. Inside this limit, we are going to multiply our expression by a form of 1, which you can always do because multiplying anything by 1 doesn't affect that value. Anything times 1 is just itself. So we'll multiply by 1 divided by a divided by 1 divided by a. Now, why is that helpful? Well, this is something that you end up doing a lot of when you work with limits in an indeterminate form, such as what we have right here. Something that can be helpful is to multiply by a form of 1 of something that is going to help simplify your expression and also make your limit easier to solve. In this case, here's what happens when we multiply by this form of 1. This will be equal to 2 times the limit as a approaches 0 from the right of negative a times the natural log of a times 1 divided by a divided by 1 divided by a. This a and this 1 divided by a will cancel out, right? Anything divided by itself is just equal to 1. So we have the negative natural log of a divided by 1 divided by a. That's what we're going to be left with in this limit. So let's just rewrite that right here. I'll show over here that this cancels out with this. And so we have the negative natural log of a divided by 1 divided by a. Okay, so now we have rewritten our limit. It's still the same limit, just expressed differently. And so now let's see what happens if we were to plug 0 in for a in this expression. If we plug 0 in, we'll have 2 times negative the natural log of 0 divided by 1 divided by 0. And that's kind of a mess, right? That doesn't look so good. The natural log of 0 is an undefined value, but we did say that as a approaches 0 from the right for the natural log, or as x approaches 0 from the right, that it gets closer and closer to negative infinity. So this would become negative infinity, but that negative would cancel out to give us positive infinity. So this would be equal to positive infinity divided by 1 divided by 0. And if you are familiar with what happens to 1 divided by x, as x approaches 0 from the right, that value gets closer to infinity, right? If you were to look at the graph of 1 divided by x, it looks something like this. And when you look at what happens as a approaches 0 from the right, or as x approaches 0 from the right, so from the positive values, as we get closer to 0 from the right, the y value of the function gets bigger and bigger. It approaches infinity. All right, so 1 divided by 0, we would say approaches infinity as a, or as x, approaches 0 from the right. So in the denominator of this expression, we have infinity. In other words, what we've got here is another limit that is in an indeterminate form, specifically infinity divided by infinity, but this is an indeterminate form that is compatible with L'Hopital's rule. So let's do that. Let's use L'Hopital's rule here. Remember that to use L'Hopital's rule, you take the derivative of the numerator and denominator separately for the expression in your limit. So let's do that here. We'll have that this is equal to 2 times the limit as a approaches 0 from the right, and then inside the limit, we'll have the derivative of the natural log of a in the numerator, and we are taking a derivative with respect to a here, and so the derivative of the natural log of a will just be 1 divided by a. But don't forget about this negative here, so what we will have is a negative 1 divided by a divided by the derivative of 1 divided by a. Now remember, 1 divided by a is the same as a to the power of negative 1, and so if you use the power rule for derivatives on that, you get negative a to the power of negative 2. You multiply the exponent down and subtract 1 from the exponent, so you have negative a to the power of negative 2. And you could then rewrite that as negative 1 divided by a squared, Just like we moved a to the first power to the numerator to make that power negative, you can move an expression with a negative power to the denominator to make it positive. Okay, so we have negative 1 divided by a squared as the derivative of 1 divided by a. So let's write that in. We have negative 1 divided by a squared. And now let's simplify. Remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So this would be equal to 2 times the limit as a approaches 0 from the right of negative 1 divided by a times negative a squared divided by 1. All right, instead of dividing by this fraction, we are multiplying by its reciprocal. We flip the numerator and denominator. Now, these two negatives will cancel out, and then we have a squared divided by a. One of those a's will cancel out, and so we're just left with 2 times the limit as a approaches 0 from the right of a. That's it. All right, this a cancels out with one of those, and so you have a divided by 1, which is just a. And so now we have a very simple limit. The limit as a approaches 0 from the right of a, we can just plug 0 in for a and get 0. So this is equal to 2 times 0, which is equal to 0. And so 0 is the value that this improper integral converges to. We can now conclude that this improper integral converges. Specifically, it converges to 0. Okay? And so if you're thinking back to earlier in the problem where we had that indeterminate form of 0 times negative infinity, you might be thinking, hey, why didn't we just say it was 0 at that point? We could have saved ourselves a lot of time and a lot of work, but that's not always going to be the case. When you have 0 times an infinite value, you cannot say that that is 0. Even though it would have given you the same answer we got here, that would have been an incorrect way of getting to this answer. Okay? You have to show all the work that we showed here to properly get to the conclusion that this integral or this improper integral equals 0. Okay, it just so happens that we got the same value as we would have gotten if we made that incorrect decision earlier in the problem. But with that, that is it for this integral. That's how you solve it. And so if you have any questions, feel free to leave those in the comments. And if you found this video to be helpful, be sure to check out some of my other Calculus 2 videos. I have all of them in a playlist that you can find on my channel. So feel free to check that out. But if you don't have any questions, then this is all I had for now. So I will see you next time.